Okay, so this first section is section 5.1 on sets. A set is any collection of objects, and an element is an object in a set. So these are kind of definitions, but actually they're not definitions. These are things that are not actually defined in mathematics. Even the Greeks understood that at some point you can't define everything. You have to have undefined terms, right? And set and element are technically undefined terms in mathematics. But for us, we're not going to need to go too difficult about why that's the case or what problems there might be. But here's an example of a set. I use the squiggly brackets is the custom. And this set is a set with three elements. A is one of the elements, B is another element, and C is the third element. Okay, so that's an example of a set. So that set has three elements. I can write this set and ... right? And it's understood here that I'm including all the natural numbers in this set. So the number 537 is an element of this set. The number 1322 is also an element of this set. But this set has infinitely many elements. It's not a finite set, it's an infinite set. Okay. So those are some examples. Another important example, especially that we're going to discover when we start learning about probability in a few weeks, is the possible sequences of tossing a coin 3 times. A set which is going to include all those outcomes. I'm going to use heads, H for heads and T for tails. So one possible outcome is to have heads, heads, heads. Right? That's one possible outcome. Okay, then we could have tails, heads, heads, or heads, tails, heads, or heads, heads, tails, 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 head, tail, head, tail, head, tail, tail, and tail, tail, tail. Right. So this set has 1, 2, 3, 4, 5, 6, 7, 8 elements. And any possible sequence of 3 coin tosses can be found in this set, because they're all that exhaust the possibilities of what there might be. Any questions? Is this clear? All right. So like I said, eventually we're going to talk about probability, and so basically the big reason why we need to talk about sets is because to learn some of these more sophisticated things, we have to be able to be comfortable with the language of set theory. Okay, so what can we do with sets? Well, one thing we can do with sets is we can take the union of sets. Okay? The union of sets. The union of sets A and B is the set containing all elements in A or in B. And the way we write it is A, this little U symbol, and then B. Okay, so that's A union B. And the set theory language way of writing this is all x's, where x is in A or x is in B. That's what we mean by a union. If we are going to draw some sort of diagram, here's set A, here's set B. The union of A and B is everything in A or in B. Right? It's everything in either of those two circles. So that's union. The other operation we talk about is called the intersection. Okay, the intersection of two sets, A and B, is the set containing all elements of A and B. Okay, to be in the intersection, you have to be in both A and B. And the way we write this is A intersect B, where that U from the union is flipped upside down now. That's the symbol for intersection. And the set theory way to write this is X such that X is in A and X is in B. All the elements that are in A and B. And of course, if we draw our diagram before, like we have A and B, the intersection is only the things that are common to both A and B. Okay, so let's do an example with unions and intersections here. Let's let the set A be the set 1, 2, 3, 4, and the set B will be the set 1, 3, 5, 7, and 11. And I want to write the union of A and B, and I want to write the intersection of A and B. And this is the type of thing that we're doing in this section, this homework, right? This is on the level of the work we're trying to do here. So A union B, the union is everything that's in either of the two. So 1 is in A and B, 2 is in A, 3 is in A and B, 4 is in A, 5 is in B, 7 is in B, and 11 is in B. Okay, that's all the things that are in A or B. So the A union B is that set there. Okay, the intersection is all the things that are in both. 1 is in both, and 3 is in both, but that is it. There are no other elements in common with A and B, both, and so the intersection is just the set 1, 3. Okay, there's a few more words that we need to talk about for this elementary set theory. The first word is subset. The set B is a subset of A if every element of B is an element of A. And the way that we write this is B is a subset of A like this, or B subset of A like that. Okay. Some books use the one with the line underneath, and some books use the one without the line underneath. Some books are actually very careful and mean different things by that. The difference would be between a less than or equal sign and a less than sign. But we're not going to be picky about that. You can use either of those two. So an example that we saw just above is that A intersect B is a subset of A, right? Because A intersect B in the one we just looked at, let's go back up, that has 1 and 3 in it. And 1 and 3 are both in A. So every element of this set here is also an element of A. And so we say A intersect B is a subset of A. So it needs to be a subset. Another important word is the empty set. This is the set with no elements. Written like that is the empty set. There's special notation for it that you might see, a 0 with a line through it. And here is a fact about empty sets. The empty set is a subset of A no matter what. No matter what A is, an empty set is a subset. Because to be a subset, all of your elements have to be in the other set. Well, there are no elements. But for logical reasons, we decide that no is the same as all. Because the checking elements in the empty set against elements of A never happens, and so there's no problem. Nothing has been violated, so we say the empty set is a subset of all sets. You can think of the empty set as a box with nothing in it. And an empty set is different from the set containing the empty set. That would be a box with a box in it. It's not the same thing. Okay, we also need to talk about what it means for sets to be disjoint. A and B are disjoint if they share no common elements. And disjoint means share no common elements. And so in particular, it's the same thing as A intersect B is equal to the empty set. Okay, so we could say two sets are disjoint if their intersection is empty. They share no common elements. Okay, here's an example using some of these concepts. Let's let A be the set containing three letters, A, B, and C. Let's find all subsets of A. Can someone give me one subset of A? Yeah, Kayla.
The empty set.
Great. The empty set counts. Perfect. Okay, can someone give me another subset of that set, capital A?
Little A.
Little a? The set containing little a, yep. Okay. Can someone give me another one?
BC.
The set containing just B and C. Great, yeah. Okay, so we can see there's a lot of subsets, right? There's a lot of subsets. And okay, well, how do we make sure we get them all, right? And so the idea is, if you think about it for a second, let's think. There's A, there's B, and C. And A we either have in the subset or we don't have in the subset. And then we consider B. B we either have or we don't. And then C. We consider whether we have C or don't have C. Yes, no. You don't have to write this whole diagram down. Just one way to think about it here. Okay, so the set down here, this set here is A, B, C. Yes, we said yes to A and B and C. This second set here would be A, B, where we have A and B but not C, and so on and so forth. And we see that there are going to be 8 possible subsets. Because we're choosing, do I want A or not? That's one choice. Do I want B or not? That's a second choice. Do I want C or not? That's a third choice. So this is 8 the reason it's 8 is because it's 2 to the third power. And 3 is the number of elements that was in the set A. And so there's a choice for each of those elements, whether you have it or not, and that's going to be all the subsets. So maybe we should write them out just to be very careful here. So we got the subset with B, the subset with C. So I'm done with one element subsets. I've got the subset with BC. How about AB? And then how about AC? So that's all possible 2 element combinations. And then I've got the set A, B, C. So I've got 1, 2, 3, 4, 5, 6, 7, 8. Got them all. And note, the empty set is down here at the end of that tree, right there. Right? No, no, no. Okay, last definition for today is that of the complement. If there is a common universe, and I'm not defining that, U understood, and A is a subset of U, then the complement of A is written this way, A prime. And it is all X in U, so that X is not in A. So it's the opposite of A. So if you draw a box for your universe, and this is your set A, the complement of A is everything outside of A. So that's the complement of A. Okay. So these objects are going to become important as we move on. We're going to learn some interesting truths about these objects that allow us to say some more complicated things that we could say before. So what is the purpose of set theory? Okay, that's a good question. It seems kind of like nonsense in some ways. It seems kind of like obvious stuff. But right, what's the purpose of algebra? The purpose of algebra, I claim, is in order to, it allows you to solve more complex multi-step problems than you could without algebra. Algebra is a way for you to organize your thinking, and using patterns of multiplying both sides by something, or things like using these tricks again and again allows us to solve much more complicated problems than we could, right? You can probably think of word problems that you have to write down the algebra to solve them, but if you just stare at the paper and you don't have a pencil, your brain can't get through it, right? And set theory is like that for things about probability and for statistics. We're not going to be able to say or explore very much without this language of set theory to do some of the work for us. So the algebra does some work for us in organizing our thinking, and set theory kind of does that as well. And it's going to pay dividends eventually when we start talking about some of these more interesting things as we go through the semester. All right, I promised one last problem here. So I'm going to write 3 sets here. U is going to be my universe. It's going to be A, B, C, D, E, F, and G. S is going to be a subset of U. It's going to be A, B, C. And T is going to be a different subset of U, A, C, D. Okay, so those are my 3 sets. I have my universe set. We're usually going to use U for this universe set. And I have my set S and my set T. I want to find a bunch of different sets related to these. I want to find the complement of S, the complement of T, the intersection of S and T, the intersection of S and T complement, S complement intersect T complement, S complement union T complement. These are the different sets I want to find. Right? So I start with this universe and these 2 sets. What other sets can be built by taking unions, complements, things like that? That's what we're trying to figure out. Okay, so S complement is everything that's in the universe that's not in S. So that's going to be D, E, F, G. Everything that's in the universe that is not in S. T complement, okay, T is A, C, D, so the complement of T is everything in the universe that's not in T. So B is not in T, E is not in T, F is not in T, G is not in T. So that's the complement of T. B, E, F, G. Okay, the union of S and T, the intersection of S and T is A and C. That's the only thing that's in both S and T. So the intersection of S and T is A and C. Now we want the complement of the intersection of S and T. Okay, so that's everything that's not in here. So that's going to be B, D, E, F, G. Okay, S complement intersect T complement. Well, I have S complement here, and T complement here, so I just need the things that are in both of them. And it looks like that is E, F, and G. And finally, the union of S complement and T complement, okay, that's going to be B, D, E, F, G. And you'll note that these two are equal. S's intersection with T, then complement, versus take the complements first of S and T and then union them. That's actually a fact called De Morgan's laws, which we will learn in the next section. Questions about this problem? Let me get it up high here so you can see that. Yeah. Any questions about this one we just did? Okay, so for the rest of the time in class, I'd like you to work on a few problems, and then if you get done, you can start in the homework. 1, 5, and 13. And then the homework is going to be 7, 9, 10, 11, 12, 14, and then 33 through 40. Okay, I promise these are, it seems like a lot of problems, but I think these ones are going to go pretty quickly for you. This is section, in case you've forgotten, this is section 5.1, and I'll leave it up here if you want to take a look at the assignment.